Here we discuss the Larmor precession of the nuclear spin. So, like other angular momenta, the nuclear spin angular momenta is also quantized in magnitude according to the expression I is equal to root of I into I plus 1 cross h. So, this is the magnitude of the nuclear spin angular momentum. And the z component of this is equal to mi cross h. So that maximum value that mi can take is plus I. So mi varies from minus I to plus I. So the maximum value is I into cross h. So Iz is always less than I. So that means the angular momentum vector will never point parallel or anti-parallel to the field. We can also verify this by drawing the diagram. For example, we consider I is equal to half. So mi can have two values, minus half and plus half. So the magnitude is of the angular momentum vector is root of I into I plus 1 cross h, and Iz is mi cross h. So the angle cos theta is equal to mi by root of I into I plus 1. So the maximum value of mi, so cos theta maximum is corresponds to when mi is I by root of I into I plus 1. But root of I into I plus 1 is slightly greater than I, and therefore I by root of I into I plus 1 is less than 1. So cos theta is never equal to 1 and theta not equal to 0. That means the angular momentum vector will never point parallel or anti-parallel to the field. And we have seen that mu is the magnetic moment due to this spin angular momentum of the nucleus is the gyromagnetic ratio times the angular momentum. So this gyromagnetic ratio depends on the nuclear G factor and Gn. So if Gn is positive, we can see that this mu and I are parallel to each other. So we can also say that the magnetic moment can never align parallel or anti-parallel to the field. So suppose we have applied field along z direction. So the magnetic moment or angular momentum vector will never align parallel or anti-parallel to the field. Only their z components are quantized such that Iz is equal to mi cross h. So mu z is gyromagnetic ratio times Iz. So the other components Ix, Iy or mu x and mu y are not quantized. They are varying such that the angular momentum vector is precessing around the magnetic field in a cone such that cos theta is mi by root of I into I plus 1. So this angle is fixed, so it presses around a cone such that Ix and Iy vary. So only Iz is quantized. So the precession of this angular momentum vector along the field direction is called the Larmor precession. So the frequency with which the Larmor precession take place is called the Larmor frequency. And on the first module, we have found that the Larmor frequency omega is equal to mu divided by I into B. So the ratio of magnetic moment to angular momentum multiplied by B gives the Larmor frequency, Larmor angular frequency omega. So substituting these values over here, and we found that mu is equal to q by mi, and substituting the values of I and all, charge and all, we found that mu is equal to Gn mu n root of I into I plus 1. So in terms of the nuclear magneton, this is the magnetic moment. So substituting it, Gn mu n root of I into I plus 1, and I here is root of I into I plus 1 cross h multiplied by b. So this root of I into I plus 1 will cancel, and we have Gn mu n b by cross h. Cross h can be written as h by 2 pi. So 2 pi into Gn mu n b by h. So the corresponding frequency, so this is angular frequency omega, the corresponding Larmor frequency is omega by 2 pi, which is equal to Gn mu n b by h. So this is the expression for Larmor frequency, and we can find that the Larmor frequency is same as that of the frequency separation between the energy levels. So we have seen that the energy separation between two consecutive energy levels in NMR, delta E, is equal to Gn mu n b. So the corresponding frequency separation is equal to delta E by h. Delta nu is delta E by h, Gn mu n b by h. So the Larmor frequency is same as that of the frequency separation between the energy levels. So in terms of this, we can explain the resonance. So resonance occurs when the frequency of the applied electromagnetic beam is same as that of the Larmor frequency of the nucleus. So this is the mechanism by which the nucleus spin interact with the beam of electromagnetic radiation. So whenever the beam has the same frequency as that of the spinning nucleus, or the Larmor frequency of the nucleus, then it can interact coherently with the nucleus, and the energy can be exchanged. So for all other frequencies, there is no interaction. So this interaction, coherent interaction, take place only if the energy of the given beam is equal to the Larmor frequency. So this is what is resonance. So we can explain nuclear magnetic resonance in terms of the Larmor frequency as well. And we have seen that the resonance can be achieved by two methods or two arrangements. So in the first method, we fix the magnetic field. So whenever we fix the magnetic field, the Larmor frequency of precession is also being fixed. So now we apply an electromagnetic radiation, and we vary the frequency of the radiation. So here we apply the same magnetic field for a set of identical nuclei. So all will have the same Larmor frequency, and when the frequency of the given electromagnetic radiation is same as that of the Larmor frequency, the resonant absorption take place. And in the second method, we fix the frequency of the electromagnetic radiation, and we vary the magnetic field. So since the magnetic field is varied, the Larmor frequency of precession also varies. So at a particular point, the Larmor frequency and the incident frequency. That means the frequency of the given electromagnetic beam equals. So at that point, resonance take place. So we have already seen that this resonance can be done in two methods. Anyway, in both cases, the frequency of the applied electromagnetic radiation is equal to the Larmor frequency. So that is the condition for resonance in terms of Larmor frequency. So now we discuss the probability of transitions. So we know that the probability of transition occurring from one state to another state is directly proportional to the population of the initial state. So we know that in the case of NMR, the upper and lower levels are equally populated, but the upper level having a slightly lesser population than the lower level. N2 by N1 is equal to e to the power minus delta E by kT. Delta E is the energy separation. So for G having positive and negative values, the separation distance is always same. So the separation distance is the modulus Gn mu n b, and this is very small value, and therefore e to the power this can be written as 1 minus this value delta E by kT. 1 minus x e to the power minus x can be approximated as 1 minus x if x is very small. So this is approximately equal to 1, but it is slightly less than 1. So therefore N1 and N2 are approximately equal, but N2 is slightly less than N1. So the upper level is having a population which is slightly less than the lower level, or lower level is having a population greater than the upper level. So since the population of the upper and lower levels are almost equal, the upward and downward transitions are induced at the same extent. The probability of upward transition and downward transition is almost same, but upward transition predominates slightly since N1 is greater than N2. So there is a net absorption of energy occur from the radiation beam. So this dominates slightly, and therefore the net effect is absorption. So the absorption and emission are having the same probability, approximately same probability, but since the population of the lower level is slightly higher than that of the higher upper level, the absorption dominates than the emission. So there is a net absorption of energy. So when we apply an electromagnetic radiation. So when the absorption predominates, there is a stage when the population of the upper and lower states become equal. So at that stage, the probability of transition, upward transition and downward transition are equal. Absorption or emission are equal, and that system is said to be saturated when N1 is equal to N2. So after this, no further absorption can take place. So this is called saturation condition, and we can re-establish the equilibrium condition, this condition, by if the system loses its absorbed energy. But it cannot do this spontaneously. There is no spontaneous emission in the case of NMR. So we have to apply some stimulation. So there is a stimulated emission only, and therefore the spectrum is called nuclear induction spectrum since it is induced. It is the emission spectrum obtained after saturation.